Hello there, and welcome to Life Beyond Seen, where curiosity slows its breathing and science settles into a quieter voice. This is a place for wondering without rushing, for questions that don't demand immediate answers, and for stories drawn from the deep past, told gently enough to let the mind loosen its grip on the day. Tonight, we're drifting toward a question that lives at the edge of imagination and evidence, somewhere between what we know and what we're still piecing together, one fossil at a time. Out there, at the bottom of the world, lies Antarctica, a continent wrapped in ice, swept by wind, and ringed by some of the coldest waters on Earth. When we picture it, we imagine silence, white horizons, and oceans so frigid they feel hostile to almost everything large and alive. And yet, the ocean has a long memory. Long before the ice sheet settled in, long before penguins shuffled across frozen shores, these waters belong to a very different world. A world where warmth reached far south, where forests grew near the poles, and where the seas were busy with enormous predators whose names still echo with a kind of awe. One of those names is Megalodon. Even if you don't follow paleontology closely, you've almost certainly heard of it. The colossal shark, larger than any predator to swim before or since. A creature whose teeth, found scattered across the globe, are often mistaken for stones or legends before they're recognised for what they really are. Megalodon has become a symbol of prehistoric power, a reminder that the ocean once held hunters beyond anything alive today. But with that fascination comes a quieter, more specific question, one that doesn't roar so much as linger. Did Megalodon ever hunt in Antarctic waters? Not in the Antarctica we know now, sealed in ice and shadowed by glaciers, but in the ancient southern oceans, when the planet was warmer, when continents sat differently, and when the boundaries between tropical, temperate and polar were far less rigid than they are today. It's a question that seems simple on the surface, but like most good scientific questions, it unfolds slowly the longer you sit with it. Before we drift any deeper, take a moment to notice where you are right now. Are you listening as the day winds down, or as the night stretches ahead of you? Are you somewhere warm, somewhere cool, or somewhere in between? And what time is it for you in your part of the world as we talk about ancient oceans that paid no attention to clocks at all? It's a small grounding thought, connecting your present moment to a story that spans millions of years. If you find this kind of exploration calming, or if it helps ease your thoughts as the day fades, you're always welcome to like the video or subscribe. It helps this quiet corner reach others who enjoy learning at a gentler pace. But for now, there's nothing you need to do except to listen. When people imagine Megalodon, they often picture it in warm sunlit waters, tropical coastlines, open oceans teeming with whales. There's a reason for that. Most of the fossil evidence we have, especially its teeth, comes from regions that are today warm or temperate. North America's eastern seaboard, parts of South America, Africa, Australia. Places that, at least now, feel like sensible homes for a massive shark that likely preferred abundant prey and relatively stable conditions. Antarctica doesn't seem to fit that picture at all, and yet the Earth Megalodon lived on was not the Earth we inhabit today. Between roughly 23 and 3.6 million years ago, during the Miocene and early Pliocene epochs, the planet was warmer overall. Sea levels were higher. Ocean currents flowed differently. Antarctica itself had not yet fully transitioned into the frozen fortress we recognise now. Ice existed, certainly, but it waxed and waned, expanding and retreating with shifting climates. To even begin answering whether Megalodon could have hunted near Antarctica, we have to let go of modern assumptions. We have to rewind the planet, mentally peeling back layers of ice, reimagining coastlines, temperatures and ecosystems that no longer exist. This isn't speculation for speculation's sake, it's how paleontology works. Fossils are fragments, and understanding them requires context, patience, and a willingness to accept uncertainty. Megalodon, scientifically known as Otodes megalodon, wasn't just a larger version of today's great white shark. It belonged to a lineage that had been evolving for tens of millions of years before humans ever appeared. Estimates of its size vary, but most place it somewhere between 15 and 20 meters long, with some suggesting even larger individuals. Its jaws could open wide enough to swallow a human whole without much effort, and its bite force likely exceeded that of any known animal. But size alone doesn't tell us where it lived. Modern sharks are surprisingly diverse when it comes to temperature tolerance. Some species remain close to warm coastlines their entire lives. Others migrate across vast distances, dipping into cooler waters when prey or breeding opportunities call them there. The great white shark, often used as a modern comparison for Megalodon, has been recorded in waters far colder than most people would expect, including regions near subpolar zones. This raises an important point. Cold water does not automatically mean uninhabitable water, especially for large predators. Still, Antarctica represents an extreme, and it always has. Even during warmer periods, southern waters pose challenges. Seasonal darkness, fluctuating productivity, and long distances between feeding grounds would have tested any marine hunter. So the question isn't simply whether Megalodon could survive cold, it's whether the ecological conditions would have made the journey worthwhile. Fossils are our primary guide here, but they're an imperfect one. Sharks, unlike animals with heavy skeletons, leave behind very little when they die. Their cartilage dissolves quickly, and what remains are mostly teeth, scattered and separated from the bodies that once wielded them. These teeth travel. They sink, get buried, get moved by currents, get exposed again millions of years later. Finding a Megalodon tooth in a particular place doesn't automatically mean the shark lived there permanently. It might have passed through. It might have hunted seasonally. It might have followed prey along migratory routes that no longer exist. So far, confirmed Megalodon teeth have not been found on the Antarctic continent itself. That absence is often cited as evidence that Megalodon never ventured that far south. But absence of evidence is not evidence of absence, especially in a place where ice covers most exposed land and seafloor access is incredibly limited. Much of Antarctica's continental shelf remains unexplored. Drilling through ice, surveying deep, cold waters, and retrieving fossils from beneath layers of sediment is an immense logistical challenge. Entire chapters of Earth's history are likely still locked beneath that ice, unseen and unstudied. There's also the matter of timing. Megalodon didn't live in isolation. Its rise and eventual disappearance were shaped by global changes, particularly shifts in climate and ocean circulation. As the planet cooled toward the end of the Pliocene, Antarctic ice sheets expanded dramatically. Ocean temperatures dropped, currents reorganized, prey species moved or declined. If Megalodon ever approached Antarctic waters, it likely did so during a narrower window, when conditions briefly aligned. That window may have been short in geological terms, leaving behind little trace. Another angle worth considering is prey availability. Megalodon is widely believed to have fed on large marine mammals, including early whales. During the Miocene, whale diversity exploded. Many species were smaller than modern whales, but they were abundant, and some followed migratory routes that may have extended into higher latitudes. Modern whales regularly travel to polar waters to feed, taking advantage of nutrient-rich upwellings that support vast populations of krill and fish. If similar patterns existed millions of years ago, it's not unreasonable to imagine Megalodon shadowing those movements, at least part of the way. Still, imagination must be tethered to evidence. Science progresses cautiously, especially when dealing with animals that have achieved near-mythic status. It's easy to let fascination outrun data. That's why paleontologists tend to speak in probabilities, not certainties, and why questions like this remain open rather than settled. As we continue, we'll look more closely at what Antarctica was like during Megalodon's time, how ocean temperatures varied, what other predators live nearby, and what modern sharks can tell us about ancient behaviour. Each piece doesn't provide an answer on its own, but together they begin to sketch the outline of a possibility. For now, it's enough to sit with the question itself. A massive shark cruising through ancient seas, far south of where we'd expect it, in waters that would one day freeze solid. Whether that image reflects reality, or remains a scientific maybe, it invites us to think differently about both Megalodon and Antarctica. The story continues, not by jumping to conclusions, but by slowly reconstructing the world these animals inhabited. One environmental shift, one fossil clue, one ocean current at a time. Long before humans ever tried to measure the ocean or name its depths, there were predators moving through it that would later feel almost unreal. Not because they belong to legend or fantasy, but because their scale stretches the limits of what the human mind is comfortable picturing. Megalodon is one of those creatures. Its reputation has grown far beyond the fossils it left behind, shaped by documentaries, exaggerated illustrations, and the natural tendency to turn the unknown into spectacle. But if we strip all that away, set aside the dramatization and the hype, what remains is still remarkable enough. A shark that truly was larger than myth ever needed it to be. To understand whether Megalodon could have hunted in southern waters, we first need to meet it properly, not as a monster, but as an animal. A living organism shaped by evolution, constrained by biology, and motivated by the same basic needs as any other predator that has ever lived: food, reproduction, survival. Megalodon did not roam the oceans to inspire fear. It swam because that is what sharks do, and it hunted because large bodies demand enormous amounts of energy. The name Megalodon comes from Greek, meaning big tooth, which is both accurate and telling. Teeth are what we know best about this shark, because teeth are what last. Thousands of them have been found all over the world, often embedded in sediment layers that date back millions of years. Some are small enough to fit in a child's palm. Others are as large as a human hand, thick, serrated, and unmistakably designed for slicing through flesh and bone. From these teeth, scientists have had to reconstruct nearly everything else. There are no complete skeletons, no preserved jaws waiting in a museum drawer, just scattered clues that require careful interpretation. By comparing Megalodon teeth to those of modern sharks, especially the great white, paleontologists have been able to estimate body proportions. These estimates suggest a creature that could reach lengths of at least 15 meters, with some calculations pushing that number closer to 18 or even 20 meters for the largest individuals. Size, however, is only one part of the picture. Megalodon was not simply a scaled-up version of a modern shark. Its teeth were thicker, its jaw structure more robust, and its bite force likely exceeded anything else the planet has ever seen. Some estimates suggest a bite force strong enough to crush whale bones with ease, and that matters, because bite force reflects diet. An animal does not evolve that kind of power unless it is regularly using it. This brings us to one of the most important aspects of Megalodon's identity. It was not a generalist feeder, it was a specialist in large prey. Fossil whale bones bearing deep bite marks match the shape and spacing of Megalodon teeth, providing direct evidence of predation or scavenging. These marks tell a story of ambush, of sudden force, of an animal capable of disabling prey far larger than itself by targeting vital areas. But even a predator this large would not hunt blindly. Energy efficiency matters. Every chase, every bite, every movement carries a cost. Megalodon would have needed environments where prey was abundant enough to justify its size. This is one reason scientists believe it favoured coastal regions and continental shelves, where marine mammals congregated and productivity was high. During the Miocene epoch, the oceans were filled with early whales, many of them smaller than modern species but still substantial in size. Some lacked the advanced speed and maneuverability of today's whales, making them more vulnerable to attack. This was a time when marine ecosystems were in flux, with new species emerging and niches being rapidly filled. Megalodon thrived in this world. Its global distribution suggests it was highly successful, occupying a wide range of ocean basins. Teeth have been found on nearly every continent, indicating a species capable of long-distance movement. This alone challenges the idea that Megalodon was restricted to narrow environmental conditions. A shark that appears on opposite sides of the planet was clearly not fragile or overly specialised in terms of geography. Still, there are limits. Even the largest predators operate within physiological boundaries. Temperature is one of them. Modern sharks are ectothermic, meaning their body temperature is largely regulated by their environment. However, some large predatory sharks, including great whites, exhibit regional endothermy. They can maintain parts of their bodies, especially swimming muscles and vital organs, at temperatures higher than the surrounding water. This gives them a significant advantage, allowing bursts of speed and improved hunting performance in cooler conditions. There is growing evidence that Megalodon may have possessed similar adaptations, possibly to an even greater degree. Its massive size alone would have helped retain heat, a phenomenon known as thermal inertia. Larger bodies lose heat more slowly, which can buffer against temperature fluctuations. Combined with potential internal heat regulation, this suggests Megalodon was not strictly limited to warm tropical waters. But again, this does not mean it could go anywhere, anytime. The concept of habitat preference is subtle. An animal might tolerate certain conditions without actively favouring them. Megalodon could have ventured into cooler waters temporarily, without establishing long-term populations there. Seasonal movement is common among large marine animals today. Whales migrate thousands of kilometres between feeding and breeding grounds. Sharks follow prey across temperature gradients that would seem extreme to land-based animals. If Megalodon followed similar patterns, its presence in a region might have been fleeting, leaving behind little fossil evidence. Another important factor is reproduction. Evidence suggests Megalodon used shallow, protected waters as nursery areas, where juveniles could grow with reduced risk from other predators. Fossil sites interpreted as nurseries tend to be in warmer coastal regions. This implies that while adults may have ranged widely, breeding likely required specific environmental conditions. That distinction matters when considering Antarctic waters. Even if adult Megalodon individuals could tolerate cooler southern oceans, those regions may not have supported the full life cycle of the species. Without suitable nursery habitats, permanent populations would be unlikely. It's also worth remembering that Antarctica itself was not always the frozen landmass we know. During parts of the Miocene, coastal areas were significantly warmer and ice coverage was reduced. Forests grew where ice now dominates. The surrounding seas would have reflected these conditions, with temperatures higher than today's Southern Ocean. In that context, the idea of Megalodon approaching Antarctic latitudes becomes less far-fetched. Not guaranteed, not proven, but plausible enough to merit serious consideration. Yet, Megalodon's image as an unstoppable super-predator can sometimes obscure an important truth. It was part of an ecosystem, not above it. It competed with other large predators, including ancient relatives of modern orcas and other macropredatory sharks. These animals may have influenced where Megalodon hunted and how it behaved. Competition can shape distribution just as strongly as temperature or prey availability. If certain regions were already dominated by efficient predators, Megalodon may have avoided them, regardless of environmental suitability. Conversely, regions rich in prey but low in competition would have been highly attractive. This balance between opportunity and constraint defines most predator behaviour, both past and present. Megalodon's extinction likely reflects what happens when that balance shifts too far. As the planet cooled, sea levels dropped, nursery habitats shrank, and new predators emerged. Smaller, more agile whales evolved, while early orcas began hunting in coordinated groups, potentially targeting Megalodon juveniles. Size, once an advantage, may have become a liability, but extinction does not erase success. For millions of years, Megalodon was one of the ocean's dominant predators. Its reign coincided with a dynamic, changing world, one where continents drifted, currents shifted, and climates oscillated between warmth and cooling. Understanding Megalodon means understanding that flexibility. It was not a creature frozen in one place or one behaviour. It adapted, moved, followed food, and responded to environmental change, at least for a time. As we continue, the focus will shift outward, away from the animal itself and toward the world it inhabited. Because whether Megalodon ever hunted near Antarctica depends as much on the nature of ancient southern oceans as it does on the shark's own biology. To answer that, we have to step back even further, to a time when Antarctica was not yet defined by ice, and the southern seas were still open to giants moving through them without knowing they were near the end of the world. To understand whether a predator like Megalodon could ever have moved through waters that would later become Antarctic, the focus has to shift away from the shark itself and toward the ocean it lived in. Not the ocean we know now, divided by rigid temperature bands and circled by powerful polar currents, but a far older version of the sea, one that behaved differently, carried heat differently, and connected parts of the planet that now feel impossibly distant from one another. The southern oceans were not always cold. That statement alone can feel counterintuitive, because modern Antarctica dominates our mental image of the south. Ice sheets kilometres thick, waters hovering just above freezing, seasonal darkness that limits productivity for much of the year. But for most of Earth's history, Antarctica was not frozen at all. Ice is a relatively recent addition to the planet's story, and when Megalodon was alive, the process of turning the South into an ice-dominated system was still underway, not yet complete. During the Miocene epoch, which spans roughly from 23 to 5 million years ago, Earth was warmer than it is today. Not uniformly, not constantly, but warm enough that polar regions supported ecosystems radically different from modern ones. Antarctica had ice, yes, but it was patchy and dynamic. Ice sheets advanced and retreated depending on atmospheric carbon levels, ocean circulation, and orbital cycles. There were long stretches of time when large portions of the Antarctic coastline were ice-free, especially during warmer intervals. The ocean surrounding Antarctica reflected this instability. Instead of being locked into a single cold regime, southern waters fluctuated in temperature and productivity. Warm currents from lower latitudes reached farther south than they do now. The barriers that currently isolate Antarctic waters had not yet fully formed. In other words, the Southern Ocean was not a sealed system. It was connected, mixed, and accessible. One of the most important developments in Antarctic ocean history is the formation of the Antarctic Circumpolar Current. Today, this current acts like a powerful moat, isolating Antarctica thermally and biologically. It flows endlessly around the continent, preventing warm equatorial waters from reaching high southern latitudes. But this current did not always exist. Its formation depended on tectonic events, particularly the opening of the Drake Passage between South America and Antarctica, and the Tasman Gateway between Antarctica and Australia. These openings did not appear overnight. They widened gradually over millions of years, altering ocean circulation bit by bit. During much of the Miocene, these gateways were still developing, meaning the circumpolar current was weaker, less stable, or not fully established. Without a strong circumpolar current, warm water intrusion into southern latitudes was far more likely. This had enormous implications for marine life. Temperature gradients were gentler, seasonal extremes were less severe, productivity patterns differed, supporting food webs that would later vanish as the climate cooled. Marine fossils from southern latitudes confirm this picture. Evidence of temperate marine organisms has been found in sediments that now sit beneath Antarctic ice. Fossil pollen indicates that forests once grew on parts of the continent. Not tropical rainforests, but dense woody vegetation that could not survive today's conditions. Where forests existed, coastal ecosystems followed. and where coastal ecosystems existed, marine food chains extended offshore. The ancient Southern Ocean was not empty or barren. It was alive, structured, and capable of supporting large predators, at least intermittently. For a creature like Megalodon, the question becomes whether these ancient conditions aligned with its ecological needs. Megalodon required large prey, likely marine mammals, and access to productive waters. It did not need warmth in the human sense, but it did need environments where prey density justified the energy cost of its size. Productivity in the ocean is driven largely by nutrient availability. Today, Antarctic waters are extremely productive during certain seasons, thanks to upwelling and the growth of phytoplankton. That productivity supports vast populations of krill, which in turn support whales, seals, and penguins. However, this productivity is highly seasonal and constrained by ice cover and light availability. In the Miocene, productivity patterns were different. Warmer waters and altered circulation would have changed nutrient distribution. There is evidence that certain parts of the Southern Ocean were productive year-round, or at least for longer seasons than today. This would have supported more stable food webs, potentially including large marine mammals. Whales, in particular, are central to this discussion. The Miocene was a critical period in whale evolution. Many lineages diversified rapidly, experimenting with body size, feeding strategies, and migratory behaviour. Baleen whales grew larger and more efficient at filter feeding. Toothed whales explored new predatory niches. Some of these whales likely ventured into higher latitudes to feed, just as modern whales do. If that was the case, then the presence of large prey in southern waters is not speculative. It is consistent with what we know about marine mammal ecology, both past and present. However, temperature still matters, even in a warmer world. The Southern Ocean, even during warm periods, would have been cooler than equatorial waters. The question is not whether it was warm by modern Antarctic standards, but whether it was warm enough for Megalodon to operate effectively. Sharks are sensitive to temperature because it affects muscle performance, digestion, and metabolism. Larger sharks, however, have advantages. Thermal inertia helps stabilize internal temperature. Regional endothermy allows bursts of speed and sustained activity in cooler water. If Megalodon shared or exceeded the thermal capabilities of modern great white sharks, it could have tolerated a broader temperature range than smaller, strictly ectothermic species. But tolerance is not preference. The ancient Southern Ocean likely represented the edge of Megalodon's viable range rather than its core habitat. It would not have been a place where juveniles thrived or where populations were dense. Instead, it may have been a region visited occasionally, seasonally, or during periods when conditions were especially favourable. This aligns with what we see in modern marine predators. Great white sharks, for example, occasionally venture into cold regions, but do not establish permanent populations there. They pass through, follow prey, then return to more stable environments. Fossil evidence of such behaviour would be sparse by nature. The geological record compounds this problem. Antarctic sediments are among the least accessible on Earth. Ice cover limits exposure. Drilling projects are expensive and rare. The seafloor surrounding Antarctica is deep, cold, and difficult to sample. Fossils that do exist may be buried far below layers that have never been reached. This means the absence of Megalodon fossils in Antarctic regions cannot be interpreted straightforwardly. It may reflect true absence, or it may reflect the simple fact that we have not looked deeply enough, long enough, or in the right places. It's also important to remember that continents move. Antarctica was not always positioned exactly where it is today. While it remained near the South Pole throughout the Miocene, subtle shifts in orientation and coastline shape would have influenced ocean currents and habitat availability. Shallow seas that existed then may now lie beneath ice or deep water, inaccessible to fossil hunters. The ocean floor itself has changed. Sediments have been subducted, uplifted, eroded, or buried. Entire ecosystems can vanish from the record without leaving a clear trace. When thinking about ancient oceans, It's tempting to imagine a static backdrop against which animals moved. In reality, the ocean is dynamic on geological timescales. Currents shift, gateways open and close, temperature gradients change, life responds, migrates, adapts, or disappears. Megalodon lived during a time of transition. The planet was cooling overall, but not yet cold. Ice was advancing, but not dominant. Ocean circulation was reorganizing, but not locked into its modern pattern. This transitional state is key. In such a world, boundaries were porous. The Southern Ocean was not yet the isolated system it would become. Predators capable of long-distance travel could exploit temporary opportunities far from their core ranges. This does not mean Megalodon routinely patrolled Antarctic waters. It means the idea cannot be dismissed outright based solely on modern conditions. There is also the matter of timescale. Megalodon existed for millions of years. During that span, conditions changed repeatedly. Even if Megalodon only ventured south during a fraction of that time, the behaviour would still fall within its ecological history. Short-lived behaviours are hard to detect in the fossil record. A species might expand its range briefly, then retreat as conditions shift, leaving little behind. Paleontology often captures long-term patterns, not brief experiments. As the Miocene progressed toward the Pliocene, global cooling intensified, ice sheets grew more stable, the Antarctic circumpolar current strengthened. Southern waters cooled further. These changes would have gradually closed the door on large warm-adapted predators. By the time Megalodon disappeared, around 3.6 million years ago, the Southern Ocean was becoming increasingly inhospitable to animals dependent on high-energy prey and flexible temperature ranges. Whether or not Megalodon ever crossed into Antarctic-adjacent waters earlier, those opportunities were narrowing. What remains is a picture of an ocean in flux, not a frozen desert, not a tropical paradise, but a shifting system where life tested boundaries and sometimes crossed them. Understanding that ocean is essential to understanding the question at hand. The story does not yet answer whether Megalodon hunted in Antarctic waters. Instead, it reframes the question. It shows that the Southern Ocean was not always a barrier. It suggests that, under the right conditions, it could have been part of a much larger, interconnected marine world. From here, the next step is to look even closer at Antarctica itself, not as a frozen continent, but as a place that once supported environments radically different from what we see today. Environments that may have briefly overlapped with the reign of one of the ocean's greatest predators. When we say the word Antarctica, the image arrives almost instantly. A continent locked in ice, endless white stretching to the horizon, winds that never seem to stop, a place defined by cold so extreme it feels timeless, as if it has always been that way. But this image, powerful as it is, represents only a thin slice of Antarctica's history. For most of its existence, Antarctica was something else entirely. Not a frozen boundary at the bottom of the map, but a living landscape shaped by warmth, water, and slow biological change. To understand whether Megalodon could ever have hunted near Antarctic waters, we have to let go of the modern continent and replace it with an older one, a version that no longer exists, but that left behind traces in rock layers, fossil pollen, and chemical signatures buried deep beneath ice and sediment. This was Antarctica before Antarctica, a place still recognisable in shape but radically different in character. Go back far enough, and Antarctica was once connected to other continents. It was part of the southern supercontinent Gondwana, joined to South America, Africa, Australia, and India. This connection mattered. It meant shared ecosystems, shared climates, and open pathways for both terrestrial and marine life. Even after these continents began to drift apart, Antarctica did not immediately freeze. Continental separation is a slow process, and climate responds gradually, not instantly. During the early and middle Miocene, Antarctica still experienced relatively mild conditions along much of its coastline. Temperatures were cooler than the tropics, but not hostile. Ice existed, but it was unstable, advancing and retreating over geological time rather than dominating year-round. Large ice sheets were present in the interior, but coastal regions often remained ice-free, especially during warmer intervals. What existed instead were forests. Fossil evidence shows that parts of Antarctica supported dense vegetation, including southern beech trees, conifers and ferns. These were not short-lived patches, but established ecosystems capable of persisting for thousands of years at a time. Forests require soil, liquid water, and relatively stable temperatures. Their presence alone tells us that Antarctica's climate once fell within a range compatible with complex life. These forests grew along rivers and coastal plains that no longer exist at the surface. Today, they lie beneath ice kilometers thick, but their chemical fingerprints remain. Fossil pollen grains, microscopic but resilient, have been extracted from sediment cores drilled deep beneath the Antarctic ice sheet. Each grain is a message from the past, confirming that Antarctica once supported a climate that feels almost impossible to reconcile with its modern state. Where forests existed on land, coastal ecosystems followed. Rivers carried nutrients into the sea, shallow continental shelves supported diverse marine life. The interface between land and ocean was active, productive, and biologically rich. These are precisely the kinds of environments that support large marine food webs. The ocean surrounding this warmer Antarctica was not the isolated, frigid system we see today. Without a fully developed Antarctic circumpolar current, warm water from lower latitudes could reach farther south. This moderated temperatures and reduced seasonal extremes. Sea ice was limited or absent during warm phases, allowing sunlight to penetrate surface waters and fuel primary productivity. In marine systems, productivity is everything. Phytoplankton form the base of the food chain, converting sunlight and nutrients into energy that supports everything else. Where phytoplankton thrive, zooplankton follow. Then fish, squid, marine mammals, and predators. The ancient Southern Ocean, under the right conditions, could sustain this entire cascade. Evidence for this comes not only from Antarctic sediments, but from surrounding regions. Fossils of marine organisms found in southern South America, Australia and New Zealand suggest interconnected ecosystems spanning much of the southern hemisphere. These organisms did not recognize modern political or geographic boundaries. They followed currents, temperatures, and food. Marine mammals were part of this picture. Early whales, seals, and other marine tetrapods were diversifying during the Miocene. Some lineages adapted to colder waters, developing insulating blubber and efficient swimming styles. Others remained more temperate, but still capable of travelling long distances. Migration likely played a role even then, linking feeding and breeding grounds across latitudes. If large whales were present in southern waters, even seasonally, they would have represented an enormous energy source. For a predator like Megalodon, such concentrations of prey would not have gone unnoticed. Large predators tend to follow predictable food sources, especially when those sources appear reliably over time. This does not mean Megalodon lived permanently near Antarctica. The ancient continent was still a challenging environment. Light availability fluctuated strongly with season. Winters brought long periods of darkness. Even during warm phases, conditions would have been less stable than in lower latitudes. These factors would have limited the time large predators could spend there. But the key point is that Antarctica was not always a biological dead end. It was once part of a continuous marine world, one that allowed movement rather than blocking it. The boundary we see today, enforced by ice and current, did not yet exist in full force. As the Miocene progressed, this began to change. Atmospheric carbon dioxide levels declined, global temperatures cooled, ice sheets grew larger and more persistent. The Antarctic circumpolar current strengthened as tectonic gateways widened. These changes reinforced one another, gradually pushing Antarctica toward isolation. This transition did not happen smoothly. It occurred in pulses. Warmer intervals interrupted cooler trends. Ice retreated, then advanced again. Sea levels rose and fell. Each shift altered habitats, opening some pathways while closing others. Animals that lived during this time had to respond to a moving target. Megalodon existed within this unstable world. It did not experience a single Antarctica, but many versions of it, each shaped by climate oscillations that unfolded over hundreds of thousands of years. During warmer phases, southern waters may have offered temporary opportunities. During cooler phases, those same waters would have become less attractive or even inaccessible. Understanding this variability is crucial. The question is not whether Antarctica was ever warm, because it clearly was. The question is whether it was warm often enough, long enough, and in the right ways to intersect with Megalodon's ecological needs. One way to approach this is to look at the timing. Megalodon appeared during the early Miocene, a time of relative warmth. It persisted through the middle Miocene, which included both warm and cool intervals. It disappeared near the end of the Pliocene, by which point Antarctic glaciation was well established, and southern waters had cooled significantly. If Megalodon ever approached Antarctic regions, the most likely window would fall somewhere in the middle of its existence, when ice was present but not dominant, and when ocean circulation still allowed warmth to reach higher latitudes. This window may have been narrow, but narrow does not mean non-existent. The geological record captures broad trends, not daily or seasonal movements. A predator passing through southern waters for a few thousand years, or even a few 100,000, might leave little behind, especially if it did not breed there or establish permanent populations. Teeth might sink into deep water, dissolve, or be buried beyond reach. Antarctica's transformation into its modern state erased much of what came before. Ice scours the landscape. Glaciers grind rock into powder. Sediments are pushed, compacted, and hidden. Entire ecosystems can be erased without a trace visible at the surface. This makes Antarctica one of the most challenging places on Earth to study paleontology. What we know comes from rare exposures, indirect evidence, and careful inference. It requires piecing together climate models, fossil distributions from surrounding continents, and chemical signals locked in ice cores and sediments. Yet, even with these limitations, a consistent picture emerges. Antarctica was once warmer, greener, and more connected than it is today. Its surrounding seas were not always hostile to large marine predators. They were part of a broader oceanic system that supported complex life. This does not prove that Megalodon hunted there. Science rarely offers proof in the form of absolute certainty, especially for deep time questions. But it reshapes what is plausible. It removes Antarctica from the category of impossible and places it firmly in the category of maybe, under the right conditions, at the right time. As the planet continued to cool, those conditions faded. Ice became permanent. Currents locked into place. Southern ecosystems reorganized around cold-adapted species. The window closed slowly but decisively. What remains is a forgotten world, buried beneath ice and time. A reminder that continents change, oceans reorganize, and even the most extreme environments were once something else entirely. Understanding that forgotten Antarctica brings us closer to understanding the full range of places Megalodon could have gone, and sets the stage for examining the physical evidence that remains, fragmentary though it may be, waiting to be interpreted. When dealing with an animal that vanished millions of years ago, there is a temptation to imagine its story written clearly in stone, waiting patiently to be read. In reality, the fossil record is less like a book and more like a scattered collection of torn pages, most of them missing, some badly damaged, others out of order. For Megalodon, nearly everything we know comes from one durable, repeatable object. Teeth. Not skeleton, not soft tissue, not even a full jaw. Just teeth, dropped one by one over a lifetime spent feeding in oceans that have since changed beyond recognition. Sharks shed teeth constantly. A single individual can lose tens of thousands over its life. For paleontologists, this is both a gift and a complication. The gift is that teeth fossilise well. They are made of dense enamel and dentine, resistant to decay, pressure and time. The complication is that teeth travel. They fall to the seafloor, are carried by currents, buried, re-exposed, shifted again, and sometimes transported far from where the animal actually lived or hunted. When a Megalodon tooth is found embedded in rock, it tells us something real, but not always something simple. It confirms that Megalodon existed at some point in that region's geological past. It does not automatically confirm how long it stayed there, how often it visited, or whether it used the area as a core habitat or a brief stop along a longer route. This distinction matters deeply when asking about Antarctic waters. The global distribution of Megalodon teeth is impressive. They have been found on every continent except Antarctica, across sediment layers dating from the early Miocene through the Pliocene. This tells us Megalodon was not a localized species. It occupied a broad range of ocean basins and was capable of crossing vast distances. That alone suggests a level of ecological flexibility that rules out a narrow, temperature-locked existence. But fossils are unevenly distributed, not because animals lived unevenly, but because preservation is uneven. Warm, shallow marine environments are excellent at producing fossil-bearing sediments. Cold, deep, or ice-covered regions are not. Much of what we know about ancient marine life comes from places that were once shallow seas and are now exposed land. Antarctica does not fit that profile. Most of the Antarctic continent is buried beneath ice sheets up to 4 kilometers thick. The continental shelf is submerged, cold, and difficult to access. Drilling projects are rare and expensive. Even when sediments are retrieved, they are often limited in scope and depth. The chances of finding Megalodon teeth there, even if they exist, are slim. This creates a bias in the fossil record. Absence of evidence in Antarctica does not carry the same weight it would in a well-sampled region like North America or Europe. The record is incomplete not because the animal was necessarily absent, but because the archive is locked away. When paleontologists map Megalodon tooth discoveries, they often see clusters along ancient coastlines and continental shelves. This makes sense. These are areas of high productivity and high fossilization potential. But between those clusters are vast gaps, including open ocean regions where Megalodon almost certainly travelled but left no trace. Teeth also vary in size and wear. Smaller teeth often come from juveniles, while larger ones belong to adults. Sites containing a high proportion of juvenile teeth are sometimes interpreted as nursery areas. These sites tend to be shallow, warm and protected. This pattern reinforces the idea that Megalodon reproduction required specific conditions. What does not follow is the idea that adults were restricted to those same areas. Adult Megalodon individuals would have ranged widely, following prey rather than staying close to nurseries. Their teeth could appear in places that were never suitable for breeding, only for feeding or passage. Another layer of complexity comes from dating. Fossil teeth are dated based on the sediment layers they are found in, not by the teeth themselves. Sediment dating is accurate on geological timescales, but it does not pinpoint exact years or even precise climate phases. A tooth found in a Miocene layer could represent a moment during a warm interval or a cooler one. Without additional context, it is difficult to say. This matters when considering Antarctica, because conditions fluctuated dramatically over time. A tooth deposited during a warm pulse might reflect very different environmental conditions than one deposited just a few 100,000 years later. There is also the issue of reworking. Sediments can be eroded and redeposited, carrying fossils from older layers into younger ones. This can make it appear as though an animal lived in a region later than it actually did. Paleontologists account for this, but it adds uncertainty, especially in dynamic marine environments. Despite these challenges, Megalodon teeth have told us a great deal. Their global spread suggests the shark was capable of tolerating a wide range of conditions. Their association with whale fossils suggests a strong reliance on large prey. Their absence from certain regions tells us less than we might like. especially when sampling is poor. There have been claims over the years of Megalodon teeth found in southern latitudes approaching Antarctica, particularly in southern South America and the southern Indian Ocean. These findings do not place Megalodon directly in Antarctic waters, but they do show that it reached high latitudes relative to the equator. The distance between those regions and Antarctica may seem vast on a map, but in ecological terms, especially during warmer periods, it may not have been prohibitive. Modern sharks regularly traverse similar distances. Great white sharks migrate from South Africa to Australia and back. They cross open oceans, dive into deep water, and encounter a range of temperatures along the way. Fossil sharks, operating in a warmer world with different current systems, may have been even more flexible. Another important consideration is that teeth represent feeding events, not daily life. A tooth embedded in sediment marks a moment when a shark lost it, likely during feeding. That feeding could have occurred at the edge of the shark's normal range. Predators often push into marginal habitats temporarily when prey availability makes it worthwhile. This means that even if Megalodon entered Antarctic-adjacent waters only occasionally, those moments might be underrepresented in the fossil record. A few teeth scattered across a vast, poorly sampled seafloor would be easy to miss. Fossils also do not capture behaviour directly. They cannot tell us whether Megalodon actively hunted in a region or merely passed through it. Bite marks on prey bones provide stronger evidence of hunting behaviour, but such fossils are even rarer, especially in polar regions. Some whale fossils show damage consistent with Megalodon bites, but these finds are mostly from temperate and subtropical regions. This may reflect true hunting preference, or it may reflect where whale fossils are most likely to be preserved and discovered. It is also worth noting that not all fossils are found where they formed. Tectonic uplift can expose ancient seafloor on land. Erosion can reveal layers that were once buried. Antarctica, by contrast, hides its past under ice, rather than revealing it. This creates an asymmetry in our knowledge. We know a great deal about Megalodon in places where geology has been kind to fossil hunters. We know far less about places where geology has been less cooperative. When scientists say there is no evidence that Megalodon hunted in Antarctic waters, what they often mean is that there is no direct fossil evidence currently available. That statement is true, but it does not carry the same force as saying Megalodon definitively never went there. Science is careful with language for this reason. Claims require evidence. Absence invites caution. Fossils also tell us something else important. Megalodon's decline and extinction coincide with major changes in marine ecosystems. As ocean temperatures dropped and ice expanded, whale communities changed. Smaller, faster whales became more common. New predators emerged, including early orcas capable of cooperative hunting. These shifts likely reduced Megalodon's access to the kind of prey it depended on. This suggests that Megalodon was sensitive to large-scale ecological change, even if it was robust in many other ways. As southern waters cooled and stabilized into a cold regime, they may have become less attractive long before Megalodon vanished entirely. So what do the teeth really tell us? They tell us Megalodon was widespread, mobile and successful for millions of years. They tell us it favoured regions with abundant large prey. They tell us it was capable of tolerating a range of conditions, though not without limits. And they tell us that the fossil record is incomplete, especially in places like Antarctica. What they do not tell us is where Megalodon absolutely never went. Teeth are clues, not confessions. They offer glimpses, not full narratives. To understand whether Megalodon ever hunted in Antarctic waters, fossils must be interpreted alongside climate models, ocean circulation reconstructions, and comparisons with modern analogues. The absence of Antarctic teeth is a piece of the puzzle, but it is not the final piece. It simply reminds us how much of Earth's history remains hidden, and how careful we must be when drawing hard boundaries around the lives of animals that lived in a world so different from our own. From here, the story naturally moves toward physiology. Fossils can tell us where an animal might have been. Biology tells us where it could have been. And that brings us to the question of cold itself. and whether a giant shark like Megalodon could tolerate temperatures that seem, at first glance, completely incompatible with its size and way of life. Cold has a way of shaping life more decisively than almost any other environmental factor. It slows chemical reactions, stiffens muscles, alters metabolism, and limits where energy can be efficiently gathered and used. For animals that live on land, the effects are obvious. Fur thickens, bodies grow larger, behaviours change. In the ocean, the rules are different, but no less strict. Water pulls heat away from the body far faster than air, and for large predators that rely on speed, power, and sustained movement, temperature becomes a defining constraint. So when the question turns to whether Megalodon could tolerate cold water, it is not a matter of imagining a shark bravely swimming through icy seas. It is a matter of physiology, physics, and energy balance. What kind of animal was Megalodon, biologically speaking, and where did its limits likely fall? Sharks, as a group, are often described as cold-blooded, but that label is misleading. Most sharks are ectothermic, meaning they do not internally regulate their body temperature the way mammals and birds do. Their temperature generally tracks that of the surrounding water. But ectothermy is not a single strategy. It exists on a spectrum, and some sharks occupy a very interesting middle ground. Large predatory sharks, including great whites, makos, and salmon sharks, possess a trait called regional endothermy. Instead of heating their entire bodies, they retain heat in specific regions, particularly the swimming muscles, brain, and eyes. This is achieved through specialized networks of blood vessels that act as heat exchangers, conserving metabolic heat that would otherwise be lost to the surrounding water. This adaptation allows these sharks to swim faster, react more quickly, and hunt effectively in cooler waters than strictly ectothermic species. Great white sharks, for example, have been recorded in waters as cold as 7 degrees Celsius, far below what most people would consider comfortable for a large fish. They do not live permanently in such temperatures, but they can function in them for meaningful periods of time. Megalodon's size alone suggests it would have benefited from similar, if not more pronounced thermal advantages. Large bodies retain heat more effectively than small ones. This principle, known as thermal inertia, means that once a large animal warms up, it cools down more slowly. In water, this can be a significant advantage, smoothing out temperature fluctuations during dives or migrations. There is indirect evidence that Megalodon may have had elevated body temperatures compared to its surroundings. Isotopic analysis of fossil teeth suggests that Megalodon maintained body temperatures higher than ambient water, similar to modern regionally endothermic sharks. While this method has limitations, it supports the idea that Megalodon was not strictly at the mercy of its environment's temperature. However, tolerating cold water is not the same as thriving in it. Temperature affects digestion. Sharks digest food more slowly in cold conditions, which means they need longer recovery times between meals. For a predator that depends on large, infrequent kills, this matters. A cold environment could reduce feeding efficiency, increasing the time and energy required to extract value from each hunt. Cold also affects muscle performance. Even with some internal heat retention, prolonged exposure to low temperatures would reduce overall efficiency. Swimming long distances, executing high-speed ambushes, and delivering crushing bites all require muscle function operating near optimal conditions. Then there is the issue of prey. Cold water ecosystems can be productive, but they are structured differently from warm ones. Prey species may be faster, more insulated, or more migratory. Hunting strategies that work in temperate waters may be less effective in polar or near-polar regions. For Megalodon, whose presumed hunting strategy involved ambushing large prey and disabling it with powerful bites, these differences could matter. If prey density was lower, or if prey species were less vulnerable, the energy payoff might not justify the effort. This leads to an important distinction. The question is not whether Megalodon could survive in cold water at all. The question is whether it could do so efficiently enough to make regular use of those environments. Modern analogues help clarify this. Great white sharks do not avoid cold water entirely, but they do not centre their lives in it either. They move through cooler regions seasonally, often following prey migrations, then return to warmer waters. They use cold environments as part of a broader range, not as a permanent home. If Megalodon behaves similarly, cold southern waters could have been part of its extended range without being core habitat. But Antarctic waters, even in warmer periods, present additional challenges beyond temperature alone. Light availability drops dramatically during winter months. Primary productivity becomes highly seasonal. Food availability may surge during certain times of year and collapse during others. Large predators can handle seasonal abundance if they are mobile. Whales do this today, travelling vast distances between feeding and breeding grounds. Sharks can do this as well, but the scale matters. A megalodon-sized animal would have needed enormous quantities of energy to sustain itself, especially if hunting opportunities were clustered into short windows. This suggests that if Megalodon ever entered Antarctic-adjacent waters, it likely did so during periods of peak productivity, when prey was abundant enough to offset the energetic costs. These windows may have coincided with warmer intervals in the Miocene or early Pliocene, when ice coverage was reduced and ocean circulation delivered nutrients more evenly. Cold tolerance is also linked to behaviour. Animals that tolerate challenging environments often do so through behavioural flexibility. They alter activity patterns, dive depths, and movement routes to manage thermal stress. Megalodon, with its size and presumed intelligence, may have been capable of such adjustments, but behaviour leaves almost no trace in the fossil record. What we do know is that Megalodon did not survive the long-term cooling of the planet. As Antarctic ice expanded and southern waters cooled permanently, Megalodon declined and eventually disappeared. This suggests that while it may have tolerated cooler conditions temporarily, it was not adapted to a world dominated by cold oceans. This is consistent with the idea that Megalodon occupied a thermal niche that allowed some flexibility but had clear limits. It was neither a strictly tropical animal nor a polar one. It lived in between, expanding or contracting its range as conditions allowed. Another factor worth considering is ontogeny, the changes an animal undergoes as it grows. Juvenile megalodons were much smaller than adults and would have been far more sensitive to temperature. They likely required warm, shallow nursery areas to survive. This creates a bottleneck. Even if adults could tolerate cooler waters, the species as a whole depended on warm environments for reproduction. This dependency would have anchored megalodon populations to warmer regions, limiting how far south they could extend without losing access to essential life stages. In other words, Megalodon could afford to visit cold waters. It could not afford to lose warm ones. This distinction helps explain why Megalodon teeth are abundant in temperate and subtropical regions and absent from polar ones. It also helps explain why the idea of Megalodon in Antarctic waters remains plausible but unconfirmed. The shark may have approached, entered briefly, or skirted the edges without leaving a lasting presence. Cold tolerance also interacts with competition. As waters cooled, new predators adapted to those conditions gained an advantage. Early orcas, for example, are thought to have been more cold tolerant and more socially complex. Cooperative hunting would have allowed them to exploit prey more efficiently in challenging environments. A solitary hunter like Megalodon, even one of immense size, may have been at a disadvantage in colder, more seasonal ecosystems where coordination and flexibility mattered more than raw power. This does not diminish Megalodon's capabilities. It simply places them within a realistic biological framework. No predator is unlimited. Every advantage comes with trade-offs. So could Megalodon tolerate the chill? Yes, within limits. Could it thrive in cold-dominated systems like the modern Southern Ocean? Almost certainly not. Could it have entered southern waters during warmer periods, following prey into regions that would later freeze? That remains within the realm of possibility. The key is to think in gradients rather than absolutes. Temperature is not a wall, it is a slope. Animals climb it as far as their biology allows, then stop. For Megalodon, That stopping point may have been farther south than we instinctively expect, but not far enough to leave clear, permanent marks in Antarctica's frozen record. Understanding cold tolerance does not settle the question. It narrows it. It tells us where to look, when to look, and what kind of presence we might expect to find. A brief visit, not a residence. An edge, not a centre. From here, the next step is to look inward, beyond temperature alone, and consider how Megalodon may have generated and retained heat in the first place. Because cold tolerance is not just about the environment, it is about what happens inside a body moving through it. When people talk about warm-blooded animals, they usually mean mammals and birds, creatures that generate their own body heat, maintain it within a narrow range, and remain active even when the environment turns hostile. Sharks rarely enter that conversation. They are filed away, mentally, with fish that drift through water at the mercy of surrounding temperatures. But this neat division does not hold up well under scrutiny, especially when the shark in question is one of the largest predators ever to live. The question of heat is central to understanding Megalodon's limits, not just whether it could endure colder water for short periods, but how its internal biology may have shaped where it could hunt, how long it could stay, and how efficiently it could function once there. This is where the idea of warm-blooded hunting enters the discussion, not as a label, but as a spectrum of biological strategies that blur the line between cold-blooded and warm-blooded life. Megalodon was not a mammal. It did not nurse its young. It did not breathe air. It did not generate heat in the same way a whale does. But that does not mean its internal temperature was simply equal to the water around it. Modern sharks show us that there is more than one way to manage heat, and size changes the equation dramatically. In the ocean, heat is lost quickly. Water conducts heat away from the body far faster than air. For small animals, this creates a tight constraint. They warm and cool rapidly, leaving little room for internal control. Large animals operate under different rules. As body size increases, surface area grows more slowly than volume. This means that larger bodies lose heat at a slower rate. Heat generated through normal metabolic activity lingers longer. This effect alone can create a form of passive temperature stability. Megalodon was enormous. Its sheer mass would have acted as a thermal buffer. Once its muscles were active, once blood was flowing and digestion underway, heat would accumulate and dissipate slowly. Even without specialized adaptations, this alone would have given Megalodon an advantage over smaller sharks in cooler water. But evidence suggests it may not have relied on size alone. Modern lamnid sharks, a family that includes great whites and makos, possess specialized vascular structures known as retia mirabilia. These are dense networks of blood vessels that allow warm blood leaving the muscles to transfer heat to colder blood returning from the gills. Instead of losing heat directly to the environment, much of it is recycled internally. This allows key regions of the body to operate at temperatures significantly higher than the surrounding water. This system does not make the shark fully warm-blooded. The skin and extremities may still match ambient temperature. But the muscles that power swimming, the brain that processes sensory input, and the eyes that track prey all remain warmer and more efficient. For a predator, that difference is enormous. Is there evidence that Megalodon possessed a similar system? Direct evidence is impossible, because soft tissue does not fossilize. But there are indirect clues. Megalodon belongs to a lineage closely related to lamnid sharks. Its teeth share structural similarities. Its presumed hunting style mirrors that of modern regionally endothermic predators. And isotopic signatures in its teeth suggest body temperatures higher than ambient seawater. Isotopic analysis works by comparing the ratios of certain oxygen isotopes in fossil teeth to those in surrounding sediments. These ratios can reflect the temperature at which the tooth formed. Studies have found that Megalodon teeth often indicate formation at temperatures warmer than the water they were deposited in. While this method has uncertainties, the pattern is consistent with internal heat retention. If Megalodon maintained elevated temperatures in key tissues, this would have expanded its functional range. Warmer muscles contract more efficiently. Warmer nerves transmit signals faster. Warmer eyes process visual information more quickly. All of this translates to better hunting performance, especially when ambushing large, fast-moving prey. Heat also affects digestion. Sharks digest food faster when warm. Faster digestion means quicker recovery between meals. For an apex predator that feeds infrequently but massively, this matters. A megalodon that could maintain warmer internal temperatures would be able to extract energy more efficiently, even when external conditions were less than ideal. But internal heat comes at a cost. Generating and maintaining it requires energy. Mammals solve this with high metabolic rates and constant feeding. Sharks do not have that luxury. Any heat Megalodon retained had to come from activity, digestion, or structural conservation, not from continuous metabolic heat production like a whale's. This creates a balancing act. Too much reliance on internal heat without sufficient food intake would be unsustainable. This reinforces the idea that Megalodon's thermal adaptations were likely situational rather than universal. They would have supported bursts of activity, migration, and temporary excursions into cooler water, not permanent occupation of cold environments. This distinction becomes crucial when considering Antarctic waters. Even during warmer periods, southern seas would have been cooler than Megalodon's core habitats. Internal heat retention could help bridge that gap, but only if prey availability justified the energy expenditure. There is also the question of how heat distribution interacts with body design. Megalodon's massive jaws, thick teeth, and heavy musculature would have required substantial blood flow. This circulation would naturally distribute heat through the body. Unlike smaller sharks, which lose heat rapidly through thin tissues, Megalodon's bulk would have slowed that process. Heat loss is not uniform across the body. Fins, tails, and extremities lose heat more quickly. Core regions retain it. For Megalodon, the core would have been vast. This could allow the animal to remain active even as peripheral tissues cooled, as long as swimming muscles and vital organs stayed warm enough. Modern great white sharks demonstrate this principle clearly. They routinely dive into cold water at depth, then return to warmer surface layers to rewarm. Their internal systems allow them to function across these gradients. Megalodon may have done the same, but on a much larger scale. Vertical movement adds another dimension. Temperature in the ocean changes with depth. Even in cold regions, deeper waters can sometimes be more stable or slightly warmer than surface layers influenced by ice and air temperature. A large shark capable of deep dives could exploit these layers strategically. This suggests that Megalodon's experience of temperature may have been more complex than a simple surface measurement. It may have moved through thermal layers, optimizing performance while minimizing heat loss. Such behavior would leave no direct fossil trace, but it fits within what we know about large pelagic predators. Another important consideration is evolutionary pressure. Adaptations do not arise without selective benefit. If Megalodon develops significant heat retention capabilities, it suggests that at some point those capabilities were useful. This implies encounters with cooler environments, whether seasonal, latitudinal, or vertical. That does not mean Megalodon evolved specifically to hunt near Antarctica. It means that its lineage encountered variable conditions often enough for flexibility to be advantageous. In a world where climates fluctuated and ocean circulation shifted, such flexibility would have been a powerful asset. But there are limits to extrapolation. Megalodon did not survive the long-term cooling of the oceans. As Antarctic ice expanded and cold conditions became permanent, the species disappeared. This tells us that whatever thermal advantages Megalodon had, they were insufficient to cope with a world dominated by cold seas. This is an important constraint. It suggests Megalodon's internal heat strategies were supplemental, not foundational. They extended its range but did not redefine its ecological niche. Warm-blooded hunters like whales operate under different rules. They They generate heat continuously. They insulate themselves with thick blubber. They can remain active indefinitely in cold water. Megalodon did not have blubber. It did not breathe air. It did not produce heat at mammalian levels. Comparing Megalodon to whales is useful, but only to highlight differences. Megalodon's strategy was one of opportunistic thermal management, not full independence from environmental temperature. This places Megalodon in a unique category. Not cold-blooded in the simplest sense, not warm-blooded in the mammalian sense. Something in between, shaped by size, activity, and evolutionary compromise. That in-between status opens doors without blowing them wide open. It allows for temporary expansion into cooler regions. It allows for seasonal following of prey into higher latitudes. It allows for brief use of environments that would later become inaccessible, but it does not support the idea of permanent residence in cold-dominated systems. It does not suggest year-round hunting beneath ice or long-term occupation of polar shells. The question of heat, then, does not answer whether Megalodon hunted in Antarctic waters. It reframes the question into something more precise. Under what conditions could Megalodon have functioned there, and for how long? The answer appears to be this. If Antarctic adjacent waters were warm enough, productive enough, and connected enough during certain periods, Megalodon's biology would not have ruled out brief use of those regions. Its internal heat retention, massive size, and predatory efficiency could have supported short-term hunting or transit. But those same traits would not have allowed it to persist once cold became the rule rather than the exception. Heat in this story is not a yes or no variable. It is a sliding scale, one that interacts with prey availability, competition, migration, and climate change. Megalodon sat somewhere on that scale, capable of pushing boundaries, but not immune to them. As we move forward, the focus shifts away from Megalodon's body and toward the bodies it hunted, because even the most capable predator is constrained by what it eats. And to understand whether Antarctic waters ever drew Megalodon southward, we need to examine what lived there, what moved through those seas, and whether the prey itself made the journey worthwhile. Predators do not choose their ranges based on temperature alone. They follow food. Everything else, physiology, tolerance, behaviour, comes second to the simple question of whether there is enough prey in a given place to justify the cost of being there. For an animal as large as Megalodon, this principle becomes absolute. Its size demanded enormous amounts of energy, and that energy could only come from dense, reliable sources of food. If Antarctic adjacent waters ever supported such sources, even temporarily, then the idea of Megalodon entering those seas stops being speculative and starts becoming conditional. To understand that possibility, we need to look beneath the surface of the ancient southern oceans and ask what lived there when the ice had not yet taken control. During the Miocene and early Pliocene, the marine world was in the middle of one of its most dramatic reorganizations. Whales were diversifying rapidly, filling niches that had never existed before. Some lineages grew larger, others faster, others more specialized in feeding strategies that exploited different layers of the ocean. This explosion of diversity did not occur evenly across the globe. It followed productivity, temperature gradients, and the availability of prey lower in the food chain. Southern oceans during ice-free or ice-reduced periods were not empty margins. They were active participants in this global transformation. The base of the food web matters first. Phytoplankton drive everything above them. In modern Antarctic waters, phytoplankton blooms are intense but seasonal, constrained by light and ice. In the past, especially during warmer intervals, these constraints were weaker. Longer ice-free seasons meant more consistent sunlight reaching surface waters. Altered circulation patterns meant nutrients could be delivered more steadily. Evidence from sediment cores suggests that parts of the Southern Ocean experienced sustained productivity during certain Miocene intervals. Microscopic fossils of phytoplankton and zooplankton appear in layers that predate full Antarctic glaciation. This indicates that the base of the food web was active enough to support larger organisms. Fish followed. Schools of bony fish and cartilaginous fish would have occupied these waters, feeding on plankton and smaller prey. Squid and other cephalopods, known to thrive in productive cooler waters today, were likely abundant as well. These organisms form the middle of the food web, transferring energy upward to larger predators. But for Megalodon, fish and squid were not the main attraction. The real draw would have been marine mammals. Whales are not evenly distributed across the ocean. They concentrate where food is abundant. Modern baleen whales migrate to polar and subpolar regions specifically to feed, taking advantage of dense seasonal blooms of krill and fish. This pattern likely has deep evolutionary roots. Even early whales, far smaller than today's giants, would have benefited from feeding in regions where energy was concentrated. The Miocene saw the rise of many whale groups that were well suited to long-distance travel. Streamlined bodies, efficient swimming styles, and growing body sizes made migration increasingly viable. Some of these whales likely followed seasonal productivity into higher latitudes, just as their modern descendants do. If whales entered southern waters to feed, even seasonally, they would have brought with them a massive influx of biomass. For a predator like Megalodon, this represents opportunity on an enormous scale. A single whale carcass contains more energy than countless smaller prey items. Even injured or weakened individuals could sustain a large predator for days. There is fossil evidence of whales in southern high latitudes during the Miocene. While direct Antarctic whale fossils are rare for the same reason shark fossils are, surrounding regions show clear signs of diverse marine mammal communities. Southern South America, Australia and New Zealand preserve whale fossils that indicate movement through southern waters. These whales did not live in isolation, their predators followed. Modern ecosystems provide useful parallels. Great white sharks are known to congregate seasonally in areas where seals haul out or where whales migrate. Orcas follow similar patterns, timing their movements to coincide with predictable prey availability. These predators are not randomly distributed. They track food across vast distances. Megalodon, with its size and energy demands, would have been especially sensitive to these patterns. It could not afford to hunt where prey was sparse or unpredictable, but where prey appeared reliably, even if only part of the year, it would have been drawn in. It is important to distinguish between different types of prey presence. Permanent resident prey supports permanent predators. Seasonal prey supports seasonal predators. Transient prey supports transient predators. Antarctic adjacent waters during warm periods likely fell into the second or third category, not the first. This aligns with what we know about Megalodon's life history. Its nursery areas appear to have been restricted to warm, shallow waters. Juveniles required protection and stable conditions. Adults, however, were free to roam. They did not need to return to nurseries except to reproduce. This creates a life stage split where adults and juveniles occupied different parts of the ocean. Adult Megalodon individuals could have followed whales into higher latitudes during feeding seasons, then retreated as conditions changed. Such behaviour would not leave clear fossil traces in those regions, especially if the visits were brief and infrequent on geological timescales. Another potential prey source comes from pinnipeds, early seals and sea lions. These animals are thought to have originated in the northern hemisphere but later spread southward. Some lineages adapted to cooler waters and coastal environments, creating additional prey opportunities in southern regions. Large fish also played a role. The Miocene Ocean supported massive schools of fish, including species larger than most modern equivalents. These fish could support large predators, either directly or by sustaining the marine mammals Megalodon targeted. Scavenging must also be considered. Megalodon is often imagined as an active hunter, but like most large predators, it likely scavenged opportunistically. Whale carcasses sinking through the water column or drifting near coastlines would have been valuable resources. Cold water slows decay, potentially prolonging the availability of such carcasses. In colder southern waters, a dead whale might persist longer than in warm tropical seas, giving scavengers extended access. This could make even marginal regions temporarily worthwhile, especially if multiple carcasses were available during migration seasons. The presence of prey does not automatically imply successful hunting. Prey behaviour matters. Cold-adapted whales may have been faster, more coordinated, or better insulated against injury. Ice cover could limit hunting strategies, especially ambush from below. Light conditions could reduce visibility. However, Megalodon's hunting strategy did not rely solely on vision. Like modern sharks, it likely used a combination of senses, including electroreception, smell, and vibration detection. These senses function in low light and murky conditions, reducing the impact of seasonal darkness. Still, prey availability would have fluctuated. Southern waters likely experienced boom and bust cycles tied to climate oscillations. In some periods, prey would have been abundant enough to attract large predators. In others, scarcity would have driven them away. This variability reinforces the idea that Megalodon's presence, if it occurred, would have been episodic, not a stable population, not a permanent hunting ground, but a region occasionally visited when conditions aligned. One more factor complicates the picture: competition. Megalodon was not the only large predator in the Miocene oceans. Other sharks, including large macropredatory species, occupied overlapping niches. Early toothed whales, some of which may have hunted cooperatively, added pressure. As waters cooled, predators better adapted to cold and capable of social hunting may have gained an advantage. In regions where prey was limited and competition high, Megalodon may have been less successful, regardless of its size. Southern waters, with their seasonal constraints, may have favoured different hunting strategies over brute force. This does not negate the possibility of Megalodon presence, it refines it. Any use of Antarctic-adjacent waters would have been shaped by a complex interaction of prey availability, competition, and environmental conditions. What emerges from this is not an image of Megalodon ruling the southern seas, but one of Megalodon responding to opportunity, moving when prey moved, pushing into new areas when the energy payoff justified it, retreating when it did not. This is how large predators behave today, and there is little reason to assume Megalodon behaved differently. The ancient Southern Ocean, during ice-free or ice-reduced periods, offered prey beneath its surface, not constantly, not everywhere, but enough, at times, to support large marine mammals and the predators that followed them. Whether Megalodon ever took advantage of that remains an open question, but the presence of prey removes one of the major barriers. Without prey, the idea collapses. With prey, it becomes a matter of timing, tolerance, and chance. From here, the story naturally shifts toward movement. If prey migrated, predators had to follow. That brings us to the invisible highways of the ancient ocean, the currents and routes that connected distant regions and made long-range movement possible for creatures willing and able to travel them. Movement is the hidden framework of the ocean. On the surface, the sea can appear vast and uniform, but beneath that appearance lies structure. Currents flow like invisible roads, connecting distant regions, redistributing heat, nutrients, and life itself. For large marine predators, these currents are not background features, they are guides. They determine where prey gathers, how energy moves, and which routes are energetically possible over long distances. If Megalodon ever approached Antarctic waters, it would not have done so by chance. It would have followed paths shaped by ancient ocean circulation. To understand those paths, we have to let go of modern ocean maps. Today's currents are the result of a planet already locked into its present configuration. Antarctica is isolated by a powerful circumpolar current. Warm equatorial waters are largely blocked from reaching the far south. This makes the Southern Ocean a distinct system, difficult for warm-adapted species to enter, and even harder to remain in. But this structure did not always exist. During much of the Miocene, ocean circulation was in transition. The continents were still settling into their modern positions. Critical gateways were open, narrowing, or only partially formed. The result was a global ocean that mixed more freely than it does today, especially between temperate and higher latitudes. One of the most important of these gateways was the Drake Passage, the stretch of ocean between South America and Antarctica. Its gradual opening allowed water to flow around Antarctica rather than being deflected northward. As it widened, it contributed to the development of the Antarctic circumpolar current. But during the early and middle Miocene, this process was incomplete. Flow patterns were weaker and more variable. Without a fully established circumpolar current, warm water from lower latitudes could leak southward. This did not turn Antarctic waters tropical, but it softened the gradient. It reduced the sharp thermal boundary that exists today. In such a system, large marine animals could move farther south without encountering abrupt environmental barriers. Another important factor was the configuration of the Tasman Gateway between Antarctica and Australia. Like the Drake Passage, this opening developed gradually. As long as it remained restricted, it limited the isolation of Antarctic waters. Together, these gateways controlled how much heat and biological material could circulate around the southern continent. For predators like Megalodon, these changes mattered enormously. Ocean currents shape prey distribution. Where currents converge, nutrients concentrate. Where nutrients concentrate, plankton blooms. Where plankton blooms, fish and squid gather. And where those gather, larger predators follow. Ancient current systems likely created seasonal or semi-permanent feeding corridors extending into higher latitudes. These corridors would not have been fixed highways like modern shipping routes. They would have shifted with climate cycles, responding to changes in temperature, wind patterns, and ice coverage. Large predators are well suited to exploiting such shifting systems. They are mobile, capable of long-distance travel, and able to respond quickly to changes in prey availability. Megalodon, with its size and energy demands, would have been especially attuned to these patterns. It could not afford to wander aimlessly. Efficient movement was essential. Modern sharks offer insight here. Satellite tracking shows that great white sharks follow specific migratory routes, often aligned with major current systems. They use currents to conserve energy, allowing them to travel farther with less effort. These routes are not random. They reflect generations of selection favouring individuals that moved efficiently through the ocean. Megalodon lived in a world where such selection pressures were just as real. Individuals that followed productive routes would have survived and reproduced. Those that did not would have perished. Over millions of years, this would have shaped population-level movement patterns. If southern waters became productive during certain times of the year, currents would have played a central role in delivering prey there and in guiding predators toward it. Warm water currents moving southward would have acted as ecological bridges, connecting Megalodon's core habitats to more marginal regions. It's important to note that migration does not require intention in a human sense. Sharks do not plan routes. They respond to gradients, temperature, salinity, prey density, and chemical cues all influence movement. Over time, these responses create patterns that look deliberate, even though they arise from simple rules. In a warmer Miocene world, those rules may have allowed Megalodon to push farther south than it ever could today. The scale of Megalodon's movement is also important. Smaller sharks may migrate hundreds or thousands of kilometers. Megalodon likely operated on even larger scales. Its size would have allowed it to store energy efficiently and travel long distances between feeding opportunities. This makes the idea of transoceanic or latitudinal movement more plausible, not less. However, large size also increases risk. Long journeys through low productivity regions carry a cost. Predators must balance exploration with efficiency. Ocean highways mitigate this risk by concentrating energy and reducing travel costs. Without them, long-range movement becomes less viable. Ancient ocean models suggest that southern circulation during the Miocene included broad, slow-moving currents rather than the fast, isolating systems of today. these currents would have been more forgiving to large migrants. They would have allowed gradual transitions rather than abrupt shifts. This kind of system favours opportunistic expansion. A predator might follow prey farther south one year, retreat the next, depending on conditions. Over geological time, such behaviour would appear sporadic and difficult to capture in the fossil record. There is also the vertical dimension to consider. Currents do not only move horizontally. Upwelling brings nutrients from depth to the surface. Downwelling transports surface waters into the deep. These vertical movements shape where prey is available and at what depths. Megalodon was likely capable of deep dives, as modern large sharks are. This would have allowed it to exploit prey moving through different layers of the water column. It also would have allowed it to encounter different temperature regimes within the same region, further expanding its functional range. The combination of horizontal and vertical movement creates a three-dimensional network of pathways. In such a network, boundaries are rarely absolute. They are gradients, zones of transition, rather than walls. Antarctica, during warmer periods, may have sat at the edge of one such transition zone, not fully integrated into the global system, but not entirely cut off either. Another factor shaping predator movement is competition. Routes that are crowded with competitors may be avoided even if prey is present. In contrast, less crowded regions may attract exploration. Southern waters, especially during early phases of cooling, may have represented underutilized space, at least temporarily. This could have drawn large predators willing to take risks in exchange for reduced competition. Megalodon, with its size advantage, may have been well positioned to exploit such opportunities, at least until other predators adapted or conditions changed. Movement patterns are also influenced by life stage. Juveniles remain in safer, warmer areas. Adults range farther. This creates asymmetry in fossil distribution. Areas visited only by adults may show fewer fossils, especially if visits were brief. Ocean highways would have been most relevant to adults, guiding them between feeding grounds. Juveniles, tied to nursery areas, would not have followed these routes. This further reduces the likelihood of finding juvenile fossils in southern regions, even if adults occasionally pass through. Taken together, ancient ocean circulation does not provide proof of Megalodon's presence near Antarctica. What it provides is a mechanism. It shows how movement could have occurred without requiring implausible leaps or extraordinary tolerance. Predators move where the ocean allows them to move. In the Miocene, the ocean allowed more freedom than it does today. As climates cooled and currents strengthened, these pathways narrowed. The Antarctic circumpolar current intensified, isolating the southern continent. Warm water routes closed. Productivity patterns shifted. Migration corridors that once extended southward became truncated. This closure would have gradually pushed predators northward, shrinking their effective range. For Megalodon, this contraction may have been one of several pressures leading to its eventual disappearance. But before that happened, there was time. Time for exploration. Time for following prey along shifting routes. Time for brief incursions into regions that would later become inaccessible. Ocean highways do not leave footprints. They leave patterns that must be inferred from climate models, fossil distributions, and modern analogues. Those patterns suggest that movement into southern waters was not impossible for large mobile predators during the right periods. Whether Megalodon used those highways to reach Antarctic-adjacent seas remains uncertain. But the highways existed. The paths were there. The question is not whether the route was open, but whether the traveller chose to take it. That question brings us closer to the modern ocean, where living sharks provide clues about how ancient predators may have behaved when facing similar choices, similar gradients, and similar risks. When evidence from deep time runs thin, the next best place to look is the present, not because modern oceans perfectly mirror ancient ones, but because living animals still obey the same physical laws, the same biological constraints, and many of the same ecological pressures. Modern sharks are not Megalodon, but they are its closest available behavioural and physiological reference points. If large sharks today can tolerate, enter, or even exploit polar and subpolar waters under certain conditions, then the idea of Megalodon doing something similar in a warmer past becomes easier to evaluate without drifting into speculation. The modern ocean is colder than it was during much of the Miocene, especially at high latitudes. Antarctica is now firmly isolated by the Antarctic circumpolar current, and sea ice dominates for much of the year. Even so, sharks are not absent from cold regions. They are simply more selective, more seasonal, and more constrained. One of the most informative examples is the great white shark. For a long time, great whites were thought to be strictly warm water predators, limited to temperate coastal regions. That picture has changed dramatically with the advent of satellite tracking. Tagged individuals have been recorded travelling thousands of kilometres across open ocean, diving to depths of over 1,000 metres and entering waters far colder than expected. Great white sharks have been documented in subpolar regions, including areas off southern South America, southern Africa, and even near the edges of the Southern Ocean. These are not brief, accidental encounters. Some individuals remain in cooler waters for weeks or months, adjusting their behaviour to local conditions. They follow prey, often seals or migrating whales, and retreat when conditions no longer favour efficient hunting. This behaviour highlights an important principle. Sharks do not avoid cold categorically, they avoid inefficiency. If cold water still offers access to high-energy prey, large sharks will tolerate it, even if it lies outside their typical range. Another example comes from salmon sharks, close relatives of great whites. Salmon sharks live in the North Pacific and are among the most cold-tolerant sharks known. They regularly inhabit waters near freezing and maintain body temperatures significantly higher than their surroundings. Their ability to do so comes from a combination of regional endothermy, high activity levels, and constant access to prey. While Megalodon did not share the same ecological niche, the existence of such sharks demonstrates that cartilaginous fish can evolve strategies that allow them to function effectively in cold environments, provided the energy balance works in their favour. Greenland sharks offer a different kind of comparison. They live permanently in cold, deep Arctic waters, often near freezing temperatures. They are massive, slow-moving, and long-lived. Their metabolism is extremely slow, and they feed opportunistically on fish, carrion, and occasionally marine mammals. They are not active pursuit predators, and their lifestyle would not suit Megalodon at all. But Greenland sharks demonstrate something else. Large body size and cold water are not inherently incompatible. What matters is how energy is acquired and used. Megalodon was an active predator, not a slow scavenger, which means its tolerance window would have been narrower. Still, the presence of large sharks in polar regions today undermines the idea that sharks as a group are excluded from cold seas. There are also observations of blue sharks, sleeper sharks, and even some hammerhead species venturing into cooler waters during certain seasons. These movements are often tied to prey distribution, rather than temperature preference. Where food goes, predators follow, even if it means entering less than ideal conditions. Modern shark behaviour also illustrates the importance of flexibility. Sharks adjust their depth, activity level, and movement patterns in response to temperature. A shark might spend time in cold surface waters, then dive into deeper layers where temperatures are more stable. It might hunt intensively during short windows of opportunity, then move on. These strategies reduce the energetic cost of cold exposure. They do not eliminate it, but they make it manageable. If we apply this understanding to Megalodon, a picture begins to form. A massive mobile predator with some capacity for internal heat retention, capable of long-distance travel, responding primarily to prey availability rather than strict temperature thresholds. In such a framework, Antarctic-adjacent waters during warmer periods would not have been categorically off-limits. They would have been marginal, seasonal, and risky, but not impossible. Modern sharks also teach us something about absence. Even today, sharks are rarely observed directly in polar waters, not because they never go there, but because observation is difficult. Ice cover, rough seas, limited daylight, and sparse human presence all reduce detection. Many shark movements are inferred only through tagging and indirect evidence. Antarctica presents an extreme version of this problem. Even if Megalodon had entered southern waters occasionally, the chances of preserving and discovering evidence are low. Modern absence of observation does not equal historical absence of presence. There is also a psychological bias at work. People tend to project modern extremes backward in time. Antarctica today feels like an absolute boundary, so it is easy to assume it always was. Modern shark distributions are constrained by currents and ice that did not exist in the same form during Megalodon's time. Modern analogues must be used carefully, but they are still informative. They show that large sharks are more flexible than once thought. They show that cold water is a challenge, not a wall. They show that prey availability can override thermal discomfort, at least temporarily. However, modern sharks also show limits. None live permanently in Antarctic waters. None hunt year-round beneath ice. Even the most cold-tolerant species have boundaries shaped by energy economics. This mirrors what we infer for Megalodon: flexibility without permanence, tolerance without specialization. One more lesson comes from how modern sharks respond to climate change. As ocean temperatures rise, shark ranges shift. Species appear in regions where they were previously rare or absent. This demonstrates how sensitive large predators are to temperature gradients, and how quickly they respond when those gradients change. During the Miocene, similar shifts would have occurred, but over much longer timescales. As warm intervals expanded southward, predators would have followed. As cooling set in, they would have retreated. Modern sharks are not relics of the past, but they are products of the same evolutionary logic. They balance energy intake against energy loss. They exploit opportunity and avoid waste. They move when movement makes sense. Seen through this lens, Megalodon does not need to be imagined as an anomaly to consider its presence near Antarctica. It needs only to be understood as a shark responding to conditions just as sharks do today. Modern behaviour does not prove ancient behaviour, but it narrows the range of reasonable possibilities. It removes the need for extraordinary assumptions. It grounds the discussion in biology rather than myth. As we move forward, the focus shifts again, this time to what we do not find. Absence, gaps, and silence in the fossil record are not empty. They carry information of their own, if interpreted carefully. And Antarctica, perhaps more than any other place on Earth, is defined as much by what it hides as by what it reveals. When scientists talk about ancient life, they often speak with careful restraint. Phrases like, "there is no evidence," or "we have not found," appear frequently. And to a casual listener, those phrases can sound definitive, as if the case is closed. But in paleontology, what we have not found is rarely the end of the story. More often, it is the beginning of a much more complicated conversation about bias, access, preservation, and the limits of what the Earth is willing to give back. Nowhere is this more true than when Antarctica enters the picture. The most common argument against the idea of Megalodon hunting in Antarctic waters is simple on the surface. No Megalodon teeth have been found there, no bite-marked whale bones, no unmistakable fossil trail pointing south. And in science, claims require evidence. Without it, caution is not just reasonable, it is mandatory. But the absence of fossils does not exist in a vacuum. It exists within a context, and that context matters enormously. Antarctica is not just another continent with poor fossil sampling. It is an extreme case, a place where nearly every condition that favours fossil discovery is actively suppressed. Thick ice sheets cover almost all exposed land. Coastal sediments that once lay in shallow seas are buried beneath kilometres of ice. The continental shelf is deep, cold, and largely inaccessible. Even where sediments exist, Retrieving them requires icebreakers, drilling platforms, and years of planning for a handful of cores. In practical terms, this means that the fossil record of Antarctica is not merely incomplete, it is mostly inaccessible. Contrast this with regions where Megalodon teeth are commonly found. Florida, Peru, South Carolina, coastal Australia. These places were once shallow marine environments and are now exposed land. Erosion, construction, and quarrying regularly bring ancient sediments to the surface. Fossils are discovered not because these places were uniquely important habitats, but because geology and human activity cooperate to reveal them. Antarctica offers no such cooperation. Even marine sediments retrieved from Antarctic waters tend to be small, localized samples. They provide invaluable climate data, microfossils and chemical signatures, but they are not designed to capture rare, large fossils like shark teeth. A single megalodon tooth lying on the seafloor could easily be missed, even if drilling occurred nearby. There is also the issue of time averaging. Fossils represent accumulation over vast spans of time. A region might have been visited by a predator repeatedly over hundreds of thousands of years, but if those visits were brief and seasonal, the chance of fossil preservation drops dramatically. Add to that the difficulty of accessing those sediments later, and the probability of discovery becomes vanishingly small. This means that saying we haven't found Megalodon in Antarctica is not the same as saying Megalodon was never there. It is saying the conditions required to find evidence there are among the worst on Earth. Absence of evidence becomes especially tricky when dealing with highly mobile animals. Megalodon was not a reef-bound fish or a bottom-dwelling invertebrate. It was a pelagic predator, moving through open water, following prey, shedding teeth into environments where preservation was unlikely. Teeth dropped into deep cold water may dissolve, be buried under fine sediments, or be carried away by currents before fossilization ever begins. Fossilization is rare even under ideal conditions. In hostile ones, it is exceptional. Another layer of uncertainty comes from how paleontologists interpret geographic ranges. Fossil distributions often reflect where animals spent the most time, not where they spent all of their time. Core habitats leave dense fossil records. Peripheral habitats leave sparse ones. Temporary excursions leave none at all. This pattern is well documented in terrestrial fossils. Many large mammals are known to have ranged far beyond their fossil-rich core areas, even though remains are only found in a subset of their actual range. Marine animals, with their fluid environments and limited preservation potential, amplify this effect. When megalodon teeth are plotted on a global map, they cluster where conditions favoured both life and fossil preservation. Gaps appear not only near Antarctica, but across large swathes of open ocean. No one argues that Megalodon avoided the open ocean simply because fossils are rare there. The same logic applies to the far south. The fossil record also reflects historical sampling bias. Scientists have spent far more time and resources studying temperate and tropical regions than polar ones. This is not a conspiracy or oversight. It is a matter of logistics and safety. Antarctic fieldwork is expensive, dangerous, and limited to narrow windows of opportunity. Entire careers can pass without a single chance to collect Antarctic marine fossils. What we know about Antarctica's past has expanded dramatically in recent decades, but it remains fragmentary. Each new drill core, each new exposure reshapes our understanding. Forests where ice should be. Warm seas where cold should dominate. These discoveries remind us how misleading first impressions can be. There is also a temporal mismatch to consider. Megalodon existed during a long span of time that overlapped with major climatic transitions. Fossils from Antarctica may represent periods either before or after Megalodon's potential presence, missing the window entirely. If Megalodon ventured south during a specific warm interval, and no sediments from that interval have been sampled, the record will remain silent. Silence, in this case, does not mean denial. It means uncertainty. Science often advances not by finding what we expect, but by realising how little we have actually looked. Antarctica is a frontier not because it is empty, but because it is hidden. The lack of Megalodon fossils there tells us more about access and preservation than it does about behaviour. At the same time, absence still carries weight. It prevents overreach. It keeps speculation grounded. Without direct evidence, we cannot claim that Megalodon hunted regularly in Antarctic waters, built populations there, or shaped southern ecosystems in the way it did elsewhere. This balance is important. The question is not whether Megalodon ruled Antarctica. The question is whether the idea can be ruled out entirely. Based on what we have not found, the answer remains no. The absence of fossils forces us to think probabilistically rather than definitively. It pushes the discussion toward likelihoods, conditions, and constraints. It shifts the focus from bold claims to careful framing. In that sense, what we have not found is as informative as what we have. It tells us where the limits of our knowledge lie. It reminds us that Earth's history is not fully written yet, especially beneath ice that has guarded its secrets for millions of years. As the narrative continues, the focus naturally turns toward change. Not just the absence of evidence, but the presence of forces that reshape the planet itself. Climate cooling, shifting currents, the gradual closing of ecological doors. To understand why Megalodon no longer exists, and why certain regions became inaccessible, we need to follow the planet as it transformed, and see how even the largest predators were carried along by changes far bigger than themselves. Extinction rarely arrives as a single dramatic moment. It unfolds quietly, unevenly, through a series of pressures that accumulate until the species can no longer adapt fast enough to keep pace. For Megalodon, the end was not sudden, and it was not caused by one catastrophic event. It was the result of a planet that was changing in ways that slowly but decisively narrowed the space in which such a giant could survive. By the late Miocene and into the Pliocene, Earth was cooling. Not uniformly, not smoothly, but with a clear long-term trend. Atmospheric carbon dioxide levels declined. Polar ice sheets expanded and became more stable. Sea levels dropped as water was locked into ice. Ocean circulation reorganized itself around these new conditions, creating sharper temperature gradients between the equator and the poles. Antarctica played a central role in this transformation. As ice coverage on the continent increased, it did more than chill local waters. It altered the entire global ocean system. The strengthening of the Antarctic circumpolar current isolated the Southern Ocean, preventing warm equatorial waters from reaching high latitudes. This isolation intensified cooling, reinforcing the growth of ice in a feedback loop that would shape Earth's climate for millions of years. For marine life, this shift was profound. Ecosystems that had once been connected became fragmented. Regions that had offered seasonal opportunity became permanently inhospitable. Productivity patterns changed, favouring organisms adapted to cold, seasonal extremes rather than those dependent on stable, warm conditions. Megalodon existed on the wrong side of this shift. Its size, once a powerful advantage, became a liability in a cooling world. Large bodies require large amounts of energy. When prey becomes less predictable or less accessible, that energy demand becomes harder to meet. As oceans cooled, whale communities changed. Some lineages went extinct. Others evolved into faster, more agile forms better suited to long-distance migration and evasion. At the same time, new predators emerged. Early orcas and other large-toothed whales developed social hunting strategies. Cooperative behaviour allowed them to exploit prey more efficiently than solitary hunters. They could target juveniles, work together to exhaust large prey, and adapt quickly to changing conditions. This introduced a new kind of competition, one that Megalodon was poorly equipped to counter. Size alone does not guarantee dominance when coordination and flexibility enter the picture. Cooling seas also affected reproduction. Megalodon's reliance on warm, shallow nursery areas meant that shrinking coastlines and falling sea levels reduced the availability of suitable breeding grounds. As ice expanded and shorelines shifted, these nurseries became rarer. Juvenile survival likely declined as a result. This created a bottleneck. Even if adult megalodon individuals could still hunt effectively in some regions, population replacement would have slowed. Fewer juveniles reaching maturity means fewer adults in the next generation, regardless of how successful the survivors are. The contraction of warm habitats also limited range flexibility. As southern waters cooled and northern regions fluctuated, Megalodon's available habitat narrowed from both ends. The margins closed in. Regions that may once have been marginal but usable, including higher latitudes during warm periods, became inaccessible. This matters for the Antarctic question. Even if Megalodon had once been capable of entering southern waters during brief warm windows, those windows closed as the planet cooled. By the time Megalodon disappeared, Antarctica had become a firm boundary rather than a flexible edge. Extinction, in this sense, is not a failure of a species. It is a mismatch between a species and its environment. Megalodon was exquisitely adapted to a world of warm seas, abundant large prey, and relatively open ocean pathways. When that world changed, its adaptations became less effective. Smaller, more flexible predators fared better. Species capable of exploiting a wider range of prey, tolerating colder water, or coordinating socially were better positioned to survive. Megalodon's specialization, once its strength, became its constraint. The fossil record reflects this transition. Megalodon teeth become rarer toward the end of the Pliocene. Their disappearance is not abrupt, but it is consistent. At the same time, fossils of modern sharks and toothed whales increase, marking a shift in apex predation. Climate change did not act alone. It interacted with biology, behavior, and competition. It reshaped ecosystems from the bottom up, altering productivity patterns that cascaded through food webs. The disappearance of Megalodon was one visible outcome of a much broader reorganization. Importantly, extinction does not retroactively define where a species could or could not go. A species can explore new regions, push boundaries, and still ultimately fail when conditions change too far. Megalodon's extinction tells us about its limits, but those limits were reached over time, not enforced from the beginning. This perspective helps frame the Antarctic question more clearly. The absence of Megalodon in modern cold oceans does not mean it could never tolerate cooler waters. It means it could not tolerate a world where cold dominated permanently. As the planet cooled, temporary opportunities vanished. Migration corridors closed. Productive seasons shortened. Ice became a constant presence rather than a seasonal fluctuation. In that world, even the largest shark to ever live could not maintain its place. Understanding extinction is not about assigning blame or imagining dramatic endings. It is about recognizing how deeply life is tied to planetary systems. Megalodon did not disappear because it was weak. It disappeared because the Earth it was built for no longer existed. With that understanding, the story moves toward its final uncertainty. Not what ended Megalodon, but what might have occurred before that end. Whether there were moments, brief and unrecorded, when it crossed into regions that would soon become unreachable. Whether, at the edge of its shrinking world, Megalodon ever passed through the southern seas one last time, following prey into waters that were cooling but not yet closed. By the time we arrive at this question, the frame has narrowed. We are no longer asking whether Megalodon lived in Antarctic waters, ruled them, or shaped them in any lasting way. The evidence does not support that, and nothing in the biology or the fossil record suggests a permanent southern stronghold. What remains is a quieter, more careful possibility. Not residence, but passage. Not dominance, but presence. Not a chapter written in stone, but a few sentences that may never have been recorded at all. Could Megalodon have passed through Antarctic-adjacent waters, even briefly? This question matters because it sits at the intersection of everything we've explored so far. Physiology suggests limited cold tolerance, but not absolute exclusion. Ancient oceans were warmer and more connected than today. Prey likely moved south seasonally. Ocean currents provided pathways. Fossil absence reflects access and preservation problems rather than definitive proof of non-existence. And extinction tells us that those opportunities closed over time, not that they never opened. What remains is probability, not certainty. Large predators do not move randomly. They respond to gradients. When prey density increases in a region, predators follow. When conditions deteriorate, they retreat. This push and pull creates edges, zones where a species may appear intermittently, never long enough to establish a stable presence, but long enough to matter ecologically in the moment. In modern oceans, these edge zones are well documented. Great white sharks occasionally appear far outside their expected range. Orcas turn up in regions where they are rarely seen. Even tropical species sometimes ride warm currents into cooler waters, then vanish again without a trace. These events often go unrecorded unless someone happens to be watching. Now extend that logic to deep time, where no one was watching, and where the record depends entirely on chance. Megalodon existed for millions of years. During that time, the planet went through multiple warm and cool phases. Sea levels rose and fell, ice advanced and retreated, ocean circulation reorganized repeatedly. If there was ever a window when southern waters became productive enough, warm enough, and connected enough to support large marine mammals, then predators that relied on those mammals would have been drawn in. This does not require Megalodon to have favoured the south. It requires only that the south occasionally offered something worth following. Seasonal migration provides a plausible mechanism. Whales today migrate thousands of kilometres between breeding and feeding grounds. They cross temperature gradients that would be lethal to many other animals. If early whales behave similarly, even at a smaller scale, they may have carried energy southward during certain seasons. Megalodon, tracking those movements, could have followed. Such following does not imply full entry into polar systems. It could have involved skirting the margins, remaining in transitional waters, entering regions that were cool but not yet locked under ice, turning back as conditions changed. Even brief presence could involve hunting. A single successful kill would have repaid the energy cost of travel. A wounded or weakened whale near the edge of its range would have been an irresistible target. For a predator built to exploit such moments, the temptation would have been strong. This kind of behaviour would be invisible in the fossil record. Teeth shed during brief visits would fall into deep water. They might never fossilise. If they did, they would be buried beneath sediments that are now unreachable. No nursery sites would form. No accumulation would occur. Just a few isolated events, scattered across time. The fossil record favours permanence. It records where animals stayed, not where they passed through. This is why the question of brief passage is so difficult to answer definitively. The tools we use to reconstruct the past are blunt when it comes to transient behaviour. Paleontology excels at revealing long-term patterns, not short-lived excursions, but biology allows such excursions. Nothing we know about Megalodon's size, metabolism or sensory capabilities rules out brief exposure to cooler waters. Its internal heat retention, while limited, would have supported bursts of activity. Its massive energy reserves would have allowed long-distance travel. Its predatory strategy, focused on large prey, would have benefited from following migratory routes, even if those routes extended into marginal environments. The constraint was not capability, it was sustainability. Megalodon could tolerate the edge. It could not tolerate the new centre once the edge became the rule. This distinction explains why the idea remains plausible without becoming exaggerated. It avoids turning Megalodon into a polar shark, which it almost certainly was not. At the same time, it avoids treating Antarctica as an eternal absolute barrier, which it was not during much of Megalodon's existence. Geography is not static. Ecological boundaries shift with climate. What feels impossible now may have been merely difficult in the past. There is also a psychological trap to avoid. Humans tend to imagine extinct animals as having rigid ranges, neatly coloured on maps. Real animals do not live that way. Their ranges blur, individuals stray, conditions vary. Over millions of years, rare events become inevitable. If Megalodon lived long enough, and the world shifted often enough, then it becomes increasingly difficult to argue that it never once approached southern waters, especially during periods when those waters were warmer and richer than they are today. That does not mean it did so often. It does not mean it did so successfully every time. It means that total exclusion is a stronger claim than the evidence supports. Science is most comfortable with gradients: likely, unlikely, possible, unsupported. The idea that Megalodon passed briefly through Antarctic-adjacent waters sits firmly in the category of possible, but unproven. And that category is not empty. It is where many truths lived before evidence caught up. What matters next is how science handles that uncertainty, not by filling it with fantasy, but by defining its boundaries clearly, by stating what we know, what we infer, and where the gaps remain. As the narrative approaches its final stretch, the focus shifts away from Megalodon itself and toward the line between evidence and speculation, where science ends, where imagination begins, and how careful we need to be when standing in that narrow space between them. Every scientific question eventually arrives at a boundary. On one side lies evidence, measured, tested, and repeatable. On the other lies speculation, informed but unprovable, shaped by logic rather than direct observation. The boundary is not a sharp line. It is a wide, uneven zone where certainty fades gradually, not abruptly. The question of whether Megalodon ever hunted or even passed through Antarctic-adjacent waters lives squarely in that zone. This is where restraint matters. Science does not advance by filling gaps with confidence. It advances by clearly marking where knowledge ends. When scientists say they cannot confirm something, they are not admitting failure. They are protecting the integrity of the process. In the case of Megalodon and Antarctica, that integrity requires holding two ideas at the same time. One, that there is no direct evidence placing Megalodon in Antarctic waters. Two, that there is no definitive evidence proving it never entered them. The tension between those ideas is uncomfortable, especially in a world that prefers simple answers. But discomfort is often a sign that a question has been framed correctly. Speculation begins the moment we move beyond what fossils, chemistry, and models can directly show. It begins when we use analogy, inference, and probability to extend known patterns into unknown territory. This is not inherently unscientific. It becomes unscientific only when speculation is presented as fact or when its limits are ignored. In this discussion, speculation arises naturally because the system itself is incomplete. The Antarctic fossil record is sparse. Ocean circulation models carry uncertainty. Biological reconstructions rely on modern analogues that are imperfect stand-ins for extinct giants. These limitations do not invalidate the inquiry, they define it. One way to recognise the boundary is to ask what would change the answer. If a Megalodon tooth were found in Antarctic marine sediment, securely dated to a time when the shark existed, the discussion would shift instantly. The question would no longer be whether Megalodon could have been there, but how often and under what conditions. The absence of such a find keeps the discussion open. Likewise, if future climate models showed that southern waters during Megalodon's time were consistently too cold or unproductive to support large marine mammals, the likelihood of Megalodon presence would drop sharply. That evidence does not currently exist. Instead, models suggest variability, with periods of warmth and productivity that complicate simple exclusion. Speculation also enters when we imagine behaviour. Fossils do not record movement paths, decision-making or hunting strategies in detail. When we suggest that Megalodon followed migrating whales southward, We are extrapolating from modern behaviour. This extrapolation is reasonable, but it is still an inference. The danger lies in forgetting that distinction. Popular portrayals often blur this boundary deliberately. They take possibility and present it as hidden truth. They frame unanswered questions as conspiracies or suppressed knowledge. This approach may be entertaining, but it undermines real understanding. A responsible approach does the opposite. It slows down. It states assumptions explicitly. It acknowledges uncertainty without inflating it. In this case, responsible framing looks like this. Megalodon lived during a time when Antarctic waters were warmer and more connected to the rest of the ocean. Megalodon was biologically capable of tolerating cooler water for limited periods. Prey likely moved into southern regions seasonally. Ocean currents provided pathways. The fossil record does not confirm Megalodon's presence in Antarctic waters, but it is also incomplete there. From these points, speculation arises naturally. It suggests that brief, intermittent presence is possible. It does not support claims of regular hunting, permanent occupation, or dominance of Antarctic ecosystems. This distinction matters because it shapes how we interpret the past and how we communicate it. When speculation is presented carefully, it invites curiosity. When it is presented carelessly, it replaces curiosity with certainty that does not belong there. Another way to locate the boundary is to consider alternative explanations. The same patterns that allow speculation also support simpler interpretations. Megalodon may never have entered Antarctic waters simply because its preferred prey did not go far enough south often enough, or because competition made those regions unprofitable, or because even brief exposure to cold reduced hunting efficiency below sustainable levels. These explanations are not mutually exclusive. They may all be partly true. Science does not demand that we choose one prematurely. Speculation also risks becoming shaped by expectation rather than evidence. Megalodon is culturally framed as a creature without limits, the largest shark, the apex predator, the ocean's ultimate hunter. That framing can subtly push interpretations toward maximum range, maximum capability, maximum dominance. Good science resists that pull. It treats Megalodon as an animal, not a symbol. Animals have limits, even the largest ones. At the same time, good science also resists unnecessary restriction. It does not impose modern conditions onto ancient worlds without justification. Antarctica today feels like an absolute barrier. Antarctica in the Miocene was not. Recognizing that difference is not speculation. It is context. Where speculation truly begins is when we attempt to fill gaps that cannot currently be filled. Did Megalodon hunt a whale near the edge of the Antarctic shelf during a warm interval? Possibly. Did it do so repeatedly, generation after generation? There is no evidence to support that. Did it ever cross a latitude line that we now associate with Antarctica? We cannot know, and it is acceptable to say that. Science does not lose credibility by admitting uncertainty. It gains it. There is also an important distinction between what is unknowable and what is simply unknown. Some questions may eventually be answered with new technology, new drilling projects, or new analytical methods. Others may remain permanently out of reach because the evidence was never preserved or has been destroyed. The Megalodon Antarctica question likely sits somewhere between those extremes. Future discoveries could tilt the balance. They could confirm brief presence, or they could reinforce absence. Until then, the question remains open. Speculation should be used not to close that question, but to frame it properly. It should help us understand what kind of evidence would matter, where to look for it, and what assumptions need testing. In that sense, speculation is not the enemy of science. Unacknowledged speculation is. This discussion also reveals something broader about how we understand deep time. The farther back we look, the more incomplete the record becomes. Certainty decreases. Context becomes essential. Questions become layered rather than resolved. That is not a weakness. It is a feature of working with a planet that has been active for billions of years. The story of Megalodon and Antarctica is not a story with a hidden answer waiting to be revealed dramatically. It is a story about limits of biology, limits of environment, limits of evidence, and limits of what we can responsibly claim. As the discussion draws toward its final stretch, what matters most is not whether we can answer the question definitively, but what the question teaches us about how life interacts with the changing planet, about how even the largest predators are shaped by forces they cannot control, and about how the boundaries we see today are the result of long histories, not eternal truths. From that perspective, the question of Megalodon in Antarctic waters becomes less about proving presence or absence, and more about understanding a world in motion, where edges shifted, opportunities opened and closed, and life responded in ways we can only partially reconstruct. That understanding carries forward into the final reflection, where the focus turns away from uncertainty itself and toward what it means to listen carefully to the silence left behind by ancient oceans, knowing that not every movement, no matter how powerful, leaves a permanent mark. As we ease toward the end of this long inquiry, it helps to pause and notice what remains when the arguments settle and the evidence stops speaking. There is no dramatic reveal waiting here, no final fossil pulled from the ice, no single sentence that resolves everything cleanly. Instead, there is quiet, the kind of quiet that fills the deep ocean long after a massive body has passed through it, the kind of quiet that forces us to listen differently. Ancient oceans do not tell their stories loudly. They do not preserve every movement or record every presence. They remember selectively, according to rules that have nothing to do with curiosity or narrative satisfaction. They remember what sinks in the right place at the right time under the right conditions. Everything else disappears. Megalodon moved through that silence once. Whether it did so near Antarctica or turned back just short of it may never be known. And perhaps that uncertainty is not a failure of knowledge, but a reminder of scale. Not just the scale of the animal itself, but the scale of time, space, and change that frames its existence. What we can say, without stretching evidence or shrinking it, is this. Megalodon lived during a period when the world was warmer, oceans were more connected, and boundaries were less rigid than they are today. It was biologically capable of pushing into cooler waters, at least briefly. It followed prey rather than maps. It responded to opportunity rather than geography. It lived within a shifting system that allowed movement, exploration, and retreat. We also know where the line was eventually drawn. Cooling seas, expanding ice, isolated currents, shrinking habitats. The same processes that shaped Antarctica into what it is today reshaped the entire marine world. Megalodon did not survive that transformation. Not because it was poorly designed, but because it was designed for a different Earth. In that sense, the question of whether Megalodon ever hunted in Antarctic waters becomes less important than the question of how fragile even dominance can be. Size did not grant immunity. Power did not override climate. The ocean did not bend to accommodate its greatest hunter. Instead, the hunter adapted as long as it could, then disappeared when adaptation was no longer enough. Listening to the silence of ancient oceans means accepting that some stories end without punctuation. There is no final scene where Megalodon turns south one last time or decisively avoids the ice. There is only a gradual fading of traces as conditions shift, and life reorganizes itself around new rules. This silence is not empty. It is full of information if we are willing to hear it properly. It tells us that absence is not always denial, that uncertainty is not ignorance, that boundaries we consider absolute are often temporary, and that the past is not obligated to resolve our questions neatly. It also reminds us of something closer to home. The oceans we know now are changing again. Currents shift, temperatures rise, species move into regions where they were once rare or absent. Others retreat. The patterns we observe today are echoes of patterns that played out millions of years ago, long before humans were there to witness them. Megalodon's story, incomplete as it is, fits into that larger rhythm. A world opens, a species thrives, conditions change, opportunities narrow, silence follows, then something else takes its place. So when we ask whether Megalodon ever hunted beneath ice-free southern seas, we are really asking how life responds to edges, how far it pushes, how long it stays, and what traces it leaves behind when it moves on. The answer, for now, remains suspended in that silence, not proven, not disproven, simply held between what we know and what the Earth has chosen not to show us. And perhaps that is fitting. Some questions are meant to slow us down rather than satisfy us, to remind us that the deep past is not a story told for us, but one we are allowed to overhear in fragments, if we listen carefully enough. Wherever you are right now, whatever time it happens to be for you, this moment exists far from those ancient oceans, and yet it is shaped by the same forces. Change, movement, limits, the quiet persistence of systems larger than any single creature that moves within them. The oceans have always carried their giants without announcing them, and when those giants are gone, the water closes behind them as if nothing passed through at all.